Right.
Okay, welcome back, everyone. We're going to start our next talk, which is the last talk before lunch. And this is a talk by Erik, Waingarten, Fast Algorithms for a New Relaxation of Optimal Transport.
Okay. Oh, well, thanks, Jelani. I want to thank the organizers and everyone's flexibility for everyone coming forward. Yeah, so I'm going to talk about fast algorithms for a new relaxation. OT stands for optimal transport. We'll get into the problems. And this is joint work with Moses Charikar, Beatty Chen, and Chris Ray. And if you guys don't know Beatty and Chris, so they're more ML systems people. And well, Chris is a professor at Stanford, and Beatty, she was also a postdoc with me at Stanford with Chris. And kind of the way that this project originated is that, well, Beatty's her research is all about building reliable systems in ML, and she uses all these sketching and locality-sensitive hashing techniques that we talk about in theory. So really, this project started as a way to see, okay, what kind of interesting questions we could ask that Moses and I are interested in, and that could potentially lead to something that they think is kind of useful. Okay. I think the most important part of this talk is really going to be an open problem that I'm going to state. So I'll state it first. And then everything I'm going to say after that is going to be just maybe epsilon amount of progress toward that open problem. But the premise is that we're going to talk about algorithmic problems of this geometric type of questions. And the premise is going to be that the fact that these problems have some degree of non-locality is going to be what makes these problems algorithmically difficult. Okay, so for now and the rest of the talk, my input is always going to be two sets of vectors, x1 through xn, that's my one set, and y1 through yn, these are vectors in RD. And you should think about what's called the so-called high-dimensional regime. And all this means is that the dimensionality d is significantly larger than log n, but less than n to the little o of 1. Okay, and we'll care about the dependence on n. And this dependence is saying, well, you don't want to be exponential in the dimension. But if you pay arbitrary polynomials in D, maybe that's OK. OK, now let me define 3 problems. And these are very related when I say it. But algorithmically, they're going to turn out to be somewhat different. And that's going to be the main open problem. So the first on the left, and these problems are going to be ordered from, I guess, my notion of least local to, from most local to least local. So the first problem is the closest pair problem. The idea is, well, you task with finding what is the pair of points, I corresponding to indexing x, and j indexing y, which minimizes the Euclidean distance between them. The second problem is maybe a slightly more complicated version of that. It's called the chamfer distance problem. And if you're here for Piotr Indyk's talk, I think tomorrow, he'll talk about an algorithm to solve this problem. This is essentially a sum of nearest neighbor problem. Okay, so you're given x and y. What is the objective? Well, you want to minimize, or in some sense, you want to compute the sum for each point xi, the distance to its nearest neighbor, yj. Okay. And lastly, and this will be kind of the main player in this talk, is the Earth mover distance. And what I think about is maybe the more complex version of this problem is that now you also want to have, for each point in x, a corresponding distance to something in y, but there's going to be a matching constraint. So I'm minimizing overall permutations pi, and the sum of distances is from xi to the corresponding matched pair in y. Yeah.
Sorry, what's the minimization over outermost?
I think this is a typo. So the first thing is, yeah. It'll be clear why I had this typo in a second. OK, so these are the three problems. And in order to highlight kind of what they are different, but for us, I'm going to write these problems as linear programs, where essentially I'm going to be optimizing over an n by n matrix, where each of these gamma ij, is going to correspond to how much we care about the pair xi with yj. OK, so all these problems, they have the variables being gamma ij for each I and j and n. So there's n squared many variables. And we want to minimize over essentially the sum of ij, gamma ij times the distance. Okay? So now the only difference in all these three problems is what constraints we impose on this matrix gamma. So for the closest pair problem, you're essentially trying to say, OK, all these gammas should be positive, and the total sum should be 1. So naturally, this will pick the minimum distance. For chamfer, you go, and if you think about the rows being indexed by x and the columns by y, then we're going through each row, and we're saying that we want to minimize this linear objective function such that the sum of every row is equal to 1. This, again, is going to pick, for each point in xi, its nearest neighbor in y. That's the minimum value of the distance. And finally, EMD, the more complicated version, is going to add not only the row constraints summing up to 1, but also this matrix has to be doubly stochastic. So the column sums also have to be 1. OK, so this is really what I'm going to mean by EMD has a very funny thing that if you have a particular solution, let's say gamma ij, and you change a particular entry, you want to increase or decrease. Well, if you want to, say, match I to j, well, whatever j was matched to, now you need to change it. And that's going to make another change. And so, I mean, if you're aware with this, the Hungarian algorithm, these exactly are the alternating cycles that you'd need to be making. And the fact that kind of a small local change can have dramatic consequences on what you need to do in order to maintain these two constraints, this makes it algorithmically very difficult to reason about. And the main question here is what can we approximate accurately in near linear time? So here I need to be very specific about what I mean by near linear time, because the input to the problem is just the n points in Rd. So the input size is n times d. But this linear program, it has n squared many variables. So even writing down this formulation of the problem, it would be too expensive. OK, so by near linear time, I really mean like n polylog n. And by approximating accurately, I mean that I want my approximations to be up to multiplicative 1 plus or minus epsilon. And the dependence on epsilon is going to be an arbitrary polynomial. OK, so I'll get more else. But roughly speaking, this is the regime that we're working with. Cool. So what's the open problem? Well, as you go from this problem over to these problems, I understand these problems less and less. And even though this problem is the least local, it still could potentially be very easy. So the first thing is that actually optimizing this is hard, in the sense that, I mean, Josh spoke about it yesterday, that if you could solve this problem in time, which is n polylog n over poly epsilon, this would break Seth. OK, so we believe that there's no such algorithms. But now when you move on to the chamfer distance, it is both hard and easy. Hard in the sense that if you actually wanted to output a solution, gamma, and by solution, because the solution is the nearest neighbors, is a sparse, the optimum, there exists a sparse solution. So you could ask, I want to output for each I the corresponding j, that's the nearest neighbor, such that the optimum will give you something which is up to 1 plus or minus epsilon, the correct thing. This is hard. This would break not Seth, but another complexity theoretic assumption. It's called the hitting set assumption. But at the same time, it's easy if all you cared about was an algorithm which could approximate the cost. So if you didn't care about outputting a sparse representation of gamma, which in theory you could, this is hard. if you just wanted to approximate this cost, it turns out there's a 1 plus or minus epsilon approximation algorithm that runs in n polylog n time. This is joint work with Ainesh Bakshi, Pyotr Indik, who's going to speak about it tomorrow, Rajesh Jairam, Sandeep, who's in the audience. So this middle problem is hard to output a solution, easy to approximate the cost of the solution. And in EMD, we don't know. So we know that it's hard in the same way that chamfer distance is hard. If I wanted to output a solution, it would break this hitting set hypothesis, the same complexity theoretic assumption. However, the open problem is I still don't know whether there exists a near linear time algorithm that can output a 1 plus or minus epsilon approximation to the cost. Okay. So I would love to solve that problem. And if anybody's interested, you also should let me know, because I'm still very interested in it. And in this talk, what I'll tell you about is how, even though we're stuck on this problem, there's a slight modification that I can make to the problem, which admits other kinds of algorithmic techniques. Yeah, and please, at any time, feel free to stop me. Yeah.
These are all multiplicative approximations.
Yeah, so it's 1 plus minus epsilon approximation to EMD within time, which is n poly log n poly d divided by poly epsilon. So I'm OK with the polynomial dependence in epsilon.
So we need to worry that the scale of the first problem is like a little different than the scale of the other problems.
Yes, that's right. So this is going to sum n distances, but this will only sum one distance. That's right. Yeah.
Yeah. What if you wanted a constant, just a constant approximation? Is it still hard?
So yeah, so that's a good question. So for a constant factor approximation, we don't know any hardness results. But we're also, there's something you can say in the regime where you're allowed slightly above linear time. So if I say like n to the 1 plus epsilon, then we know how to design algorithms which are roughly approximation O of 1 over maybe square root epsilon. Now, I mean, this, I'll get into it in a second. This will be like another kind of regime and like a large approximation regime where we can say something interesting. All right, so here's the outline of the remainder of the talk. So first, I'm going to tell you about this so-called spanner approach. And this is the kind of in line with what Cliff was asking. This is the one technique that we have in order to solve these problems up to, say, some large constant factor approximation or even larger approximations, which at a high level are reductions to graph problems. So we take our geometric problem. This is some linear program, but you could express it as a graph. The spanner approach is a way to reduce to a graph problem such that you can solve the corresponding graph problem. And then I'll tell you about kind of another line of work from the more applied ML community where they also change the optimal transport problem, where they're not studying this Earth mover distance problem, but they're introducing a different kind of objective. It's called the synchron distance. And that's going to be very related to the kind of goals that we set for ourselves. And then I'll tell you the main result and how we were able to kind of do something different and what that different is. OK, so here's the spanner approach. And I'm encapsulating the entire spanner approach by this one theorem of Harpalet, Indik, and Sidropoulos in 13. But you should really think about it as a way to reduce my geometric problem to a sparse graph problem, so a graph that doesn't have n squared many edges, such that the corresponding solution on the graph will correspond to the geometric problem up to some approximation. And here the theorem says that if you want to build a graph which has that its distances is a C approximate, it approximates a distance in the graph up to factor of C of the original distance, then you can build a graph in time which is n to the 1 plus O of 1 over C squared. So as you allow a larger approximation C, this overhead on linear time is going to go to 0. But for any fixed constant, it's still some constant. And the fact that you can do this in this amount of time means that the number of edges in the graph that you produce has at least at most those number of edges. And now I don't have like a precise theorem for this statement, but it turns out to be the case that for a lot of these geometric questions, not only the closest pair or chamfer or this EMD, there's a very close relationship between the time complexity of building these graphs, of doing these reductions to graph problems, and the time that it takes to solve the approximate nearest neighbors problem. So, I mean, this is not a formal statement, but it turns out that the way that you solve for build these graph spanners, what you end up doing is you end up essentially building polylog many approximate nearest neighbor data structures. And then you query that data structure n times in order to like locally connect each point to a few of its neighbors. So here, that's what the expression is, that usually the time complexity is the n times the query time for approximate nearest neighbors, plus the time that it takes to build this data structure. Okay? And the truth is that we don't know how to get very accurate approximations for approximate nearest neighbors when the underlying dimension is high. So we don't have, say, polylog time algorithms or n polylog n space data structures that get accurate 1 plus epsilon approximations. So in this regime of 1 plus epsilon approximations, we have to pay this polynomial overhead in the spanner constructions. And I think this is really, well, for us, it was kind of a conceptual challenge and something that when we started talking to Beatty and Chris, it was really something that this was maybe the point of contention, is that the conceptual challenge is that these accurate approximations essentially end up taking quadratic time. If you do want to build a spanner where this factor of c is something like 1 plus epsilon, you're going to start seeing running times which are like n to the 2 minus some function of epsilon. This is something that Josh spoke about yesterday as well. And yeah, like I said, it's not only for the optimal transport. If you want to output solutions for, say, the Euclidean minimum spanning tree, the closest pair, and all these problems, they'll essentially run in time n to the 2 minus epsilon, or to order epsilon, or some function of epsilon. Except there's one problem, and this problem has already come up in this workshop a few times, of the kernel density estimation problem, where there are some instances where we can get 1 plus or minus epsilon approximations in running times which are near linear. OK, so these were really our motivating kind of questions. And oh, let me tell you about kind of synchron distances. What do people do? So OK, so in theory, we oftentimes study the Earth mover distance. And we have, if we want fast algorithms, we really end up with crude approximations by setting this factor c to be large and using the spanner approach. On the other hand, if you look at the machine learning literature, then they change the problem slightly. And I won't get into the precise definition, but it's something that also feels like optimal transport. They get very accurate additive approximations. So if you think of all your points as lying within, say, a ball of radius r, they can approximate the value of this optimal transport synchron problem up to plus or minus epsilon r. So it's an accurate approximation if you're allowed to be additive. But the algorithms are quite slow. Essentially, they have to materialize this entire n squared many distances. Essentially, they work on this matrix gamma directly. So our motivating questions were, OK, from the theory side, can we break away from this spanner approach? Can we build some techniques? And maybe more generally, we are flexible in the definition of the problem. Say, OK, so synchron, they have already changed the problem. So which kind of transport can we develop algorithms for? Okay. So now I'll tell you kind of what our relaxation is. So the main idea was to focus on a slight perturbation of EMD. And OK, this is another typo. We should think about these encode my constraints, that the row sums should be equal to mu plus. The column sums should be equal to mu minus. And I'm rewriting the Earth mover distance problem by saying, well, let me first consider this vector, which I'll call the cost vector for gamma, which is an n squared dimensional vector. And for entry ij, I'm just going to give you the cost that this linear program pays for this particular setting of gamma. So this should be gamma ij, how much mass you send from I to j, times xi minus, okay, this should be yj. And then Earth mover distance is just the minimum over gamma, satisfying this constraints of the L1 norm of this cost vector. So yeah, so that's just a reformulation of the problem. And our twist is to say, okay, we won't solve the Earth mover distance problem, but what we are going to solve is, instead of looking at the L1 norm, minimize the L1 norm over gamma, we're going to minimize the L rho norm of this cost vector. Okay, so my new problem is to say, okay, I want to minimize over these matrices gamma, which are bigger than 0, such that I minimize the L rho norm of this cost. Okay? So if I write it down, this just looks like a sum over each entry ij, gamma ij times the distance raised to the power rho, all raised to the 1 over rho. Yeah.
Should I think of rho? Plus epsilon, 100, half.
Yeah, so rho is going to be something bigger than 1. And the reason why this was our compromise is to say that as rho approaches 1, whatever you output is going to approach the Earth mover distance. But it's going to turn out that for every setting of rho, this problem is algorithmically much easier. Any questions on the formulation? I think this is probably one of the most important things. Okay, cool. Now, maybe you're familiar with a different kind of optimal transport that's called the Wasserstein P distances. They're very similar. They're very similar to EMD, but they want you to minimize the sum of powers of distances. Now, this looks related, but it's different, because in Wasserstein P, you don't raise gamma ij to power p. You're just saying my costs are now distances to some power. For us, it's very important that we raise the variable gamma ij to power rho, and this makes the problem just a different problem. That's why it's going to be algorithmically easy. For the same reasons, we don't know how to solve EMD in near linear time. We also don't know how to solve these Wasserstein P distances in near linear time. Yeah.
So if you look at the objective function, if you look at this objective function for the first time, it's hard to know. Maybe it's worthwhile saying, how should one think of the optimum solutions to this problem relative to EMD? Is there a way to think about how the solutions differ?
So like how intuitively we think about
Yeah,
these?
intuitively.
Yeah, so okay, good. So what is the goal? The goal is to minimize this thing. And now when you're trying to, let's think of the cost vector. When you're trying to take the L1 norm of a cost vector, you're just taking the sums of the entries. But now if before that, I raise each entry to the power rho, I essentially want to make sure that your entries aren't big. I can spread them out as much as possible. Because if I take, let's say, a vector which sums up to 1, the L1 norm, but now I compute the L2 norm, if the entries were kind of spread out, then this will be significantly smaller. So this optimization problem is trying to find ways to kind of send mass from the points xi to xj, which minimize this objective in a way that it also encourages you to send your mass out to other points. Now, you can come up with you can relate multiplicatively the objective, the true value of this quantity and the true value of this quantity. And this is because the L rho norm is related to the L1 norm. And that would give you an approximation of rho as going to 1. Essentially becomes n squared to the power of 1 over rho. No, 1 over rho minus 1. Some quantity. As rho goes to 1, this thing approaches this, and you can come up with the what multiplicative approximation would you be getting. But these multiplicative approximations are not super interesting because they're polynomial approximations. So it would be strictly dominated by the spanner approach. If you really cared about this problem, the best thing we know is still the spanner approach. But for this different problem, that's going to be algorithmically easier. Okay. So let me tell you just the main theorem, which is just an algorithm for this, this new objective function, this new relaxation. And the new theorem says that for any row where I set row bigger than 1, and any epsilon, so I'm going to get these accurate epsilon approximations, there's an algorithm which receives as input these two sets of points. And in time, which, OK, this expression is a little bit complicated to parse, but there's n, so that's our linear time. And the overhead is going to be a small polynomial of rho, for which as rho goes to 1, this gets arbitrarily close to 0. Something that's going to depend exponentially in 1 over rho minus 1. So as rho goes to 1, this term is going to be the thing that blows up, divided by poly epsilon. So these are going to be the epsilon accurate parameter. And it's going to output an additive epsilon r approximation. So all my vectors live in a ball of radius r. Okay. So I'm changing the problem in a few ways. First, and most importantly, I changed the objective. Now, as rho goes to 1, this thing approaches EMD, but my running time is going to blow up because this term, this exponential in 1 over rho, this quantity becomes very small, and hence this exponential becomes very large. But we can approximate up to some plus or minus epsilon r, something that we don't know how to do with EMD. Yeah.
I have 2 questions. So as rho is large, this is also
As rho is large, this is also expect like if rho is 2, this could be like arbitrary polynomial in n.
Yeah. So yeah, good. So it is also true that when our algorithm, and I think this is a weakness of our algorithm, the running time, it's important that rho be bigger than 1. If it's too close to 1, it blows up. And if it's further than 1, it also blows up.
Okay, and then like one other quick question is, if you didn't power up the gammas, it didn't matter if you changed the Euclidean distance to like Euclidean distance to the row. You said the hardness results carry over. It is the same in your formulation. Like, does it matter that you change the distance to the Euclidean distance? Like, if you had just powered up the gammas and not powered up the norms, would it have affected anything?
That's a good question. I don't know. Yeah. Yeah.
If rho is really large, do you know that the problem is hard? Because it seems like it might be easy, right? Because it's sort of like becomes like a threshold problem, almost, right?
So, okay.
Just wondering. I know not this algorithm, but the problem in general. Right? Rho is large.
Yeah, I could. Yeah, I don't know. I would have. Let's maybe talk about that.
Okay.
Yeah. But I wanted to just post one parametrization of rho, where I think kind of highlights the newness. If you think of rho as something like 1 plus 1 over square root log n, now you are getting near linear or almost linear time algorithms, which get additive plus or minus epsilon r approximations to a different problem. Let's do it.
Just 2 quick clarifying questions. First of all, is this outputting an approximation to the optimal cost, or is this outputting an approximate solution?
Yeah, that's a good question. So it will only output an approximate solution. And the reason is that for these cases, you don't know that the optimal rho is sparse. Sorry, the optimal gamma, the optimal like assignment. Now gamma is the minimum over these matrices, and they're all kind of non-negative, and it's going to have small entries, but they could be sparse. Now, for the min-cost matching question for EMD, you know that the optimal gamma is going to be sparse, so you could hope to output a solution. It turns out to be hard. But for this problem, we can't hope to output the solution, because the solutions may not be sparse.
Okay, so it does output the near optimal score then, not
Correct.
the, okay.
Yeah.
Great. And also, can you remind me what little r is?
Yeah, little r is going to be the radius. So let's think about r as all these points. are within distance at most r. So the biggest value that this could take would be each point has the point r.
Gotcha.
So the scale of the problem is maybe r times n.
Thank you.
So following up on that, do you have like query access to this matrix? Like if I just care about the 1, 3 entry, can
Yeah.
this algorithm give you
Yeah.
that value?
Yes, yes, we do. And also, let me say that what I said before is slightly wrong. If we're taking the sums of distances, then the scale of the problem is epsilon is r times n, because we're summing n distances, which could be from 0 to r. And our approximate, I'm missing a factor of n here. So it's additive epsilon with respect to the scale of the problem. So this is our concession. In a way, there are these fast algorithms for computing EMD, but they get large, crude approximations. On the other hand, we have these synchron type of algorithms. These are slow. These take quadratic time, but they achieve this additive epsilon Rn approximation. So, well, this is another class of optimal transport problems, which you can say something that looks like the synchron running times, synchron kind of approximations, but at the same time have running times which look like the very fast EMD algorithms. Okay. So now let me tell you about why this problem is different and why we can solve it and why this minor change makes a big change algorithmically. And it's related to this problem that there were some talks yesterday on the kernel density estimation. And I'll tell you about kind of the relationship between the two. OK, so I'm going to go through this slide pretty quickly because Moses' talk yesterday kind of introduced the problem. So what is a problem? The kernel density estimation, well, it's a problem where you have some data set, x1 through xn, and there's going to be a kernel function. And you should think about this function as some function that decays as the points x and y get further away from each other. So for instance, one possible kernel function is something like 1 over the distance squared. Okay. Now, what's the goal? The goal is to design a data structure that can store these points such that in the future, a new point is going to come. And your goal is to approximate the average value. So as kind of Moses said yesterday, you're trying to say, what is the aggregate force that each of the points, x1 through xn, is exerting on the point, on the query point y. And there's been some work on this kernel density estimation problem. I'm not going to get into it, but I think there's been some works that carry a very strong conceptual message that this notion of smoothness, or how exactly this function k decays as a function of distance, is very helpful for solving these kind of problems. So in particular, I'm referring to this paper of Bakurs, Charikar, and Smilakis, who showed that if you have a kernel where this function k decays polynomially with the distance, so it's something like, in this case, this would be a degree s smooth kernel, then there exist data structures for approximating KDE in time, which are going to be polylog in n with a to 1 plus minus epsilon approximations, with a parameter which grows exponentially, but only in the smoothness parameter s. So that's the main message. And I guess I think about this problem that you have like the data set points. Each point introduces some kind of decay around it, and your queries should be able to spot for any particular query point what is the sum of the data set points contributing to that point. Okay. The connection between this problem and our L row problem, this relaxation, is going to be that we're going to be able to set this parameter, the smoothness parameter in the kernel, to be exactly rho over rho minus 1. And we're going to reduce the problem of optimizing this convex program defined with this L row norm minimization to that of solving the kernel density estimation, and then just use these data structures. Now, I want to just say, okay, because this is a sketching workshop, this is not super surprising that smoothness makes it easier to solve a problem with like sampling or sketching methods. In fact, I mean, the traditional, like, first thing I learned about sketching was the sketching for LP norms. And there's also the case that the complexity of how well you can compress or how well you can sketch these vectors depends on this parameter p, where the non-smoothness of the LP norm, so that when p is infinity, it's very sensitive to whether a particular entry is large or small. That's going to be the value that you're optimizing. Then sketching these quantities becomes harder. So it's another way in which smoothness in the objective makes it very easy for sampling and sketching based methods. Okay, so now I'll tell you kind of what was the main technical component, I guess, of how do we use these kernel density estimation subroutines to solve this modified optimal transport problem. And here I'm going to just post back the linear program for the Earth mover distance. And I do want to say that if you look at the literature of like the spanner approach or these algorithms for EMD, the linear program doesn't play a very like prominent role because the size of this linear program is quadratic. We can't even write it down. But somehow even representing the solution gamma is complicated. But when we modify the problem to our L row problem, it's going to turn out to be very useful to look at what this linear program looks like. OK, now the reason why I can't represent this linear program because it's too big, I can't even hold the solution gamma. But the linear program has two n many constraints. Right? One constraint for each row and one constraint for each column. So if instead you looked at the dual of this linear program, then each constraint will now correspond to a variable and each variable to a constraint. So the number of variables in the dual will be 2 times n. Okay? So already now I've made progress because I can at least hold a solution. Okay, so in a way, if you think of, instead of minimizing this quantity, optimizing this over some variables alpha and beta, which correspond to the constraints on the rows and the constraints on the columns, at least now I can hold on to an alpha and beta and try to make progress on that. The challenge, of course, is that now I have n squared many constraints. So it's hard for me to determine whether a particular alpha or beta is in this feasible set of solutions for the dual. Now, when you write what happens to our modified problem, so I've just changed now the objective to minimize this L row to the row quantity. That still has this objective function, has these 2n many constraints. So the dual will have also 2n many variables. However, the constraints are no longer these n squared many constraints. But rather what you get is you get one aggregated quantity which measures how much you don't satisfy the constraint. So if instead you wanted to minimize this quantity, right, the dual of this, it'll look like something that was very similar to before. However, instead of having these n squared many constraints, you say for each constraint, you're going to have some measure of how much you're violating the constraint. So let me just go before. Before, the constraints were saying that for each pair of points, alpha I and beta j, they can't be further away than the distance. Now I'm going to allow you to set alpha and j arbitrarily. But if you do set them to be bigger than the distance, I'm going to penalize you in the objective function. Okay. So here's the term. When alpha I minus beta j is bigger than the distance, then this expression now becomes bigger than 1. And this gets raised to the power s. So as s gets larger and larger, each time you are bigger than 1, you get penalized even more for it. So if you were twice as big as the distance, you're going to pay a factor of 2 to the s.
Sorry, what is this? This is the dualism article?
Yeah, OK, good. Oh, sorry. Yes, s is going to be set exactly to the dual norm of, yeah, exactly, yeah. Good. So yeah, so then the thing to notice is that this looks very much like a smooth kernel type of problem. Okay, in some sense, we have a set of points, x, and we're interested in how much does y, these, if you squint your eyes and you forget about these two terms, alpha minus beta, then this is just aggregating for each point y, what is like the sum of 1 over distance to the power s. Okay, good. So really, the picture looks like the following. Let me compare the two. I have here the dual for the EMD. These are the variables alpha and beta, and each distance gives me a constraint of alpha minus beta. And I would say find that point. And here, the only difference is that these n squared many constraints are getting aggregated together. They factor into the objective. So the picture now is that at any particular point alpha and beta, which you can hold on to, every wall of this polytope is essentially contributing, it's hurting your objective. So, okay, in this case, maybe the optimum is here. If you happen to step out, then this sum here would be very big. This becomes negative, and it's hurting your optimization. You're going to move away from this. Okay, and the punchline is that using kernel density estimation, we can just run first order method. So we can run gradient descent by just computing what is the gradient at every particular point, and then taking a step in the opposite direction. Okay, and here is just that the fact that if you compute the gradient in alpha I and beta j, then this exactly looks like, well, some constant that depends on the 1 over n, and something that looks like a smooth kernel up to these alpha and beta entries, which you hold on to. Okay, so in the paper, we show that, well, if you can handle alpha I minus beta j, this positive term, which we give a data structure to solve this problem, then the rest is a smooth kernel, and you can kind of estimate the gradient in polylog time. So in n polylog n space, in time, we can approximate the gradient. We can just run gradient descent. Okay. Are there any questions? Yeah.
So, I mean, like if I think of say S as 4 or 10,
Yeah.
right? Gradient descent doesn't really do great, right? Because the moment you are below in the less than 1 regime, your gradients vanish basically, and like you don't get convergence to like anywhere one. You don't even get poly 1 or epsilon convergence. So do you have a translation from estimating gradients to?
So maybe this is the reason why our algorithm, it also performs poorly if rho is substantially bigger than 1. So it's important for us that rho is close to 1, but not, so it's bigger than 1, but not too far from 1. So yeah, in our analysis, this is where we're using the fact that at some point, if rho is set to some fixed value bigger than 1, then yes, S, the corresponding dual norm, will be something that is bigger than 2. And if it's some fixed constant, then we have to pay some overhead in n. But yeah, I mean, it did.
Okay, I mean, yeah, maybe we can take it offline. But basically, like once you are at, well, like if rho is 1.1, S looks like 10 or 11, and then the gradient vanishes so rapidly that once you get into the flat gradient regime, you will never basically go to 0, because you need like really large step sizes, even in a one-dimensional problem. So you have to do something to compensate for the fact that gradients vanish as a very high power of how far you're from the distance. So unless rho is exactly 2, it's not clear to me why vanilla gradient descent with a constant step size would converge. So I'm wondering if you have a modification.
No, we don't have any modification, though. We can see. I mean, we'll have to, yeah, let's talk about it. But,
Does gradient descent need to converge or just get a good solution in your term?
yeah, I mean, we just need to stop when we can prove that whatever solution we have, it's a plus or minus epsilon r times n. Oh, okay. Yeah, so let me wrap up. I think this was pretty much it. I can just say the open problems. first open problem is just, can we beat the spanner approach? I started out this talk with an open problem, which I still don't know how to solve. But this is kind of an orthogonal direction where we can algorithmically do something new and something that goes beyond the spanner approach using these kernel density estimation theorems. Okay, again, what other geometric problems can we approximate the cost for accurately? I think there's a paper of Shumai and Zoller that they show how to approximate the cost of the Euclidean minimum spanning tree. So there are other kinds of geometric problems for which you can get good approximations to the cost using other kinds of techniques. And finally, our dependence on epsilon is quite bad. And one thing that Chris and Beide really care about is that if you're actually running these methods in practice, you need to have something that is not meaningless for epsilon being at 0.01 or something. But still, the main open problem I'll leave up. This is to give an algorithm for approximating the cost of EMD in time which is near linear, or to show that doing so would break some complexity theoretic assumption.
Eric, just one comment. For the synchron algorithm, you mentioned that it gives an additive epsilon r, but actually it does that for a modification of the objective, which is sort of a entropy normalized.
Yeah. So the synchron algorithm for the synchron distance gets an additive epsilon r.
So that body of work modifies the objective in some way.
Yeah.
And it turns out it's fine. It seems to work well in practice, but all the convergence results are for this modified objective.
That's right.
And so this is a different modification.
Yes.
Any other questions for Erik?
So at the end of the day, the dual problem you're solving is sort of the exact dual problem for the row norm problem, right?
Yeah.
Is there a particular, and it's running gradient descent, I feel like there's results out there where you know how to get a relative error result for linear program solving or like convex optimization solving it, right? Like where do we end up having to pay an additive error instead of something like multiplicative?
Yeah, that's a good question. We tried using these techniques. We couldn't quite get them to work, but it's very possible that you can get a multiplicative error for this problem.
Okay.
Yeah.
Just like conceptually feels like this algorithm should be able to push it out, or do you think there would be like an algorithmic adjustment to make that happen?
The specific algorithm. Maybe you may need to change these algorithms. Actually, the algorithms that you're referring to, I think they solve the problem up to some small epsilon, and then they change the problem a little bit, solve it to compute the difference. And they do this until some time where they use a crude algorithm. So, I mean, they do change the algorithm.
Okay, cool. Thank you.
Okay. Any other last question? If not, let's thank Erik again. And today